Good morning. This is Sunday. It's September 18th, and we are headed into week 4 of our online astronomy course. Um, I will tell you that this is the last module. Module 4 is the last module of the set of the first 4 modules. And after that, we'll have our first exam. So this coming week, you'll be working on Module 4. And the week after that, starting on September 26th and running through October 2nd, you'll have your first exam. It has 35 multiple choice questions. It is open book. You can use your book. You can use your homework quizzes, and 35 multiple choice questions. You won't need a calculator, but you can have a calculator handy if you want one, just in case, but you won't need it. And what else can I tell you? Oh, yes, you can take the exam twice if you want to. You can take it the first time, then you can look on Canvas and see which questions you missed. And then knowing that and looking up the answers, you can take it again and try to raise your score. And if you take it twice, I give you the average of your 2 attempts. So, what is in Module 4? Module 4 is all about light. And astronomers have to be experts at using light because all they can do is look at light from the stars and look at light from galaxies and things like that. I mean, yes, we've sent spacecraft to our sun, and we've sent spacecraft to study all the planets in our solar system, as well as dwarf planets and asteroids and comets. But as far as sending a spacecraft to study another star, no, too far away. But we can look at the light from those stars. And so astronomers are really experts at getting every piece of information they can from the light they receive from sources in the sky. So what is light? First of all, what is light? I mean, we all have looked at light all our life. That's all we've ever seen is light, of course. But what is light made of? And light is made of vibrating electric and magnetic fields, waving electric and magnetic fields. Now, you all know what a magnetic field, if you have a compass or a magnet, maybe you've picked up a paper clip with a magnet before, or maybe you've used a compass to orient yourself to Earth's magnetic field and find the direction of north. So you know what a magnetic field is. And you've also had the expansion of the experience, I wanted to say, the experience of using static electricity. Maybe you have taken clothes out of the dryers, and when you come near the clothes, maybe the hairs on your arm stand up a little bit, and that's due to the electric field that surrounds all charged objects. So that's what light is made of. Light is made of both electric fields and it's made of magnetic fields. So it's sort of like this, electric fields and magnetic fields. And those fields are perpendicular to each other and they wave through space. What really is happening is that they're pointed in one direction, then they weaken and they point in the opposite direction, then they weaken and point in the opposite direction. So the electric field is always moving up and down. The magnetic field is always moving up and down. And those two are always perpendicular to each other. So that's what light is. Light is waving electric and magnetic fields. And you might wonder, well, how do you describe a light wave then? It's waving in magnetic fields. Well, like any wave, if you have any wave that's just going along, It has high points and low points. It has peaks and troughs. And the distance to one peak to the next peak down is called the wavelength of the light. Yeah, the length of the wave. Now, the first person to really understand what comprises visible light, what is visible light made of, not the electric and magnetic fields, that was to come later, but Isaac Newton was the first person to really break white light, sunlight, into its component colors. And he did this by holding up a prism. A prism is just a little triangular piece of glass. And when light passes through that prism, it's broken into its component colors, just like raindrops break sunlight into its rainbow spectrum of colors. And you can see that rainbow behind me right now. You can see all the colors of the rainbow from red all the way down through violet. So red through violet, all the colors of the rainbow. And what distinguishes red from violet or green from blue? What makes yellow yellow? And the answer is the wavelength of the light determines the color of the light. So red light has the longest wavelength. The wavelength of red light is about 700 what? 700 nanometers. The wavelength of light is incredibly tiny. And so we have to use a small unit to talk about it. And in light, we talk about billionths of a meter. A nanometer is a billionth of a meter. And the wavelength of red light is 700 nanometers. Now, the wavelength of violet light is about 400 nanometers. So the visible spectrum, and the spectrum is what we call the collection of all of the wavelengths of light. The visible spectrum goes from about 400 nanometers, and that is on the low wavelength side, the blue side, the violet side, all the way up to 700 nanometers on the red side. Now, you might wonder, well, is that all the light there is? And the answer is no. People remember the triangular piece of glass I said that Newton used to break sunlight into its component colors? Well, other people tried that, and it seemed reasonable to them to put thermometers in that light and measure the temperature of the red and blue lights. But when they put the thermometer beyond the red, so what they would do is they would put the thermometer in these colors and then put it beyond the red, you still got a temperature rise. And that told them that there were colors beyond the red. And today we call that infrared light. And there are also shorter wavelengths than violet, and we call those ultraviolet. And in fact, today we know the total electromagnetic spectrum. Remember, I said that light has waving electric and magnetic waves. So we can talk about light as being an electromagnetic wave. And the total spectrum of that light is called the electromagnetic spectrum. And it goes from very short wavelength gamma rays. Then the wavelength increases from gamma rays to X-rays to ultraviolet through violet, then the visible spectrum to red, and then infrared, and then microwaves, and then radio waves. Yes, radio waves are light waves. You might have thought, if you listen to the radio, you're listening to sound. So some people think that radio waves are sound waves. No, radio waves are light waves. And those radio waves, those electromagnetic waves, are sent from the station through the air. They hit the antenna, and that produces a current in the antenna. And that current causes your speaker to vibrate. and that produces the sound waves you hear. But the radio waves themselves are light waves. And so are the microwaves. You're cooking with light in your microwave oven. So really amazing. And we'll come back to microwaves. You might think, oh, do microwaves have a use in astronomy? And around the end of the course, we'll see that yes, microwaves play a very important role in astronomy. And in fact, the entire electromagnetic spectrum plays an important role in astronomy. But there's a problem, and that is our atmosphere absorbs a lot of the light that tries to come in from the sun, because the sun gives off all sorts of light, all the colors. But not all those types of light come in through our atmosphere. Some are absorbed by Earth's atmosphere, and so we have to send spacecraft and telescopes that are sensitive at those wavelengths into space. So the James Webb Space Telescope that just went up studies infrared light. And we've set up satellites to study microwaves. And we sent them to study gamma rays and X-rays. And at every wavelength we've looked, we've found amazing things, and we'll be learning about those in the course. But let's get back to sunlight. Okay. Sunlight, as you know, is composed of all of these colors that you see behind me here, all of these colors and more. So where does sunlight come from? Well, right now we're just going to talk about the light that reaches Earth, the sunlight emitted from the sun's surface. And we'll talk about later, when we talk about the sun, what generates that light. But the sun is a big ball of hot gas. It's a big, dense ball of gas. And it turns out that any object with a temperature above absolute zero, and that includes you, it includes me, all objects have a temperature above absolute zero, and all objects, that means, emit electromagnetic waves, emit light with a certain characteristic spectrum. And that spectrum is called the black body spectrum. A black body is just an object that doesn't reflect any light of its own. It only heats up and emits light because of its temperature. And we call those objects black bodies, and stars are black bodies, to a very good approximation. Now, in this module, there are 3 videos, and one of them is about black body radiation. So please take a look at that, and you'll see how black body radiation works. So what else can astronomers learn from light? Well, if we look at the black body radiation, we can find out the temperatures of stars. And in fact, it turns out that if you increase the temperature of a black body, like a star, you get out more blue light. So blue stars are hotter. And if you decrease, if you look at cooler stars, those stars are redder. So a hot black body emits more blue light, and a cooler black body emits more red light. Now, this is sort of backwards, you know. We always think as blue, we associate blue with ice and being cold, and we associate red with fire and being hot. But no, in astronomy, it's the opposite. Hotter objects give off more blue light. Cooler objects give off more red light. How about us? We're giving off black body radiation. But, you know, if I turn out the lights, we'd all be in the dark and we couldn't see each other. But if I had an infrared camera, I could see you all because we are all glowing in infrared light. In fact, we're giving off net about 100 watts. We are giving off as much energy as a 100-watt bulb does. But that energy is not visible. and so we can't see it. Now, as I said, what else can astronomers learn from light? Well, if you really look at the spectrum of the sun, if you really spread out the sunlight and you take a close look at it, you see a lot of dark lines in that spectrum. So dark line cutting through just certain colors. Certain colors are gone. And that's because certain atoms in the sun's atmosphere can absorb the continuous spectrum of all colors from the sun's surface. And those atoms in the sun's atmosphere absorb just certain colors. And by looking at the pattern of those absorbed wavelengths in the sun's spectrum, we can tell what elements are present in the sun. We can tell what the sun's made of by studying its light. Same thing for other stars. We can tell what other stars are made of by studying their spectrum. And then this module, you'll learn why atoms absorb and emit light. Some of the prettiest things in the sky are atoms that have absorbed energy and then emit light. And you'll learn about how atoms do that in this module. And there are also videos about how atoms absorb and emit light that I've made for you to watch. So please do that as well. Finally, in this module, there's 2 chapters, and the second chapter that's in this module is about telescopes. Now, I'm not going to worry about telescopes so much. You should know a couple of things about telescopes. What is a telescope? Why do telescopes have to be so big? Why do we want larger telescopes? Well, telescopes are just light buckets. They collect light. And you can imagine if you took a rain bucket outside to collect rain, you'd rather have a large rain bucket to collect a lot of rain than a smaller rain bucket to just collect a little bit of rain. Same thing, there's light pouring in from the stars. And so we want a big light bucket, a big telescope. And collecting that light makes images brighter. And that means we can see more distant objects. Also, there's another advantage to having a larger mirror. And most modern telescopes, you'll find out, use mirrors to create the main image. But there's another advantage to using a large mirror, and that is you have better resolution. Now, the resolution is the ability to separate 2 closely spaced objects. Now, if I were to move my fingers back and keep moving them back into the background there would come a point where you couldn't separate them. Or maybe a better example that you've noticed is that if you've ever been driving out on the desert at night and it's a long road and you're looking ahead of you and you see a car's headlights, maybe you can't see if that's a motorcycle with just 1 light or a car with 2 lights because the car's so far away and the lights blend together. The ability to separate 2 closely spaced light sources is called resolution. And the larger the telescope, the better the resolution, the better the telescope can separate 2 closely spaced images. So please find out about that. And I've included a video about the James Webb Space Telescope. First of all, how amazing it was to package up this telescope and then have it unfold in space to create a really large infrared telescope in space. And another video just to show you, there's an astronomer in England, and she'll talk about some of the first images that JWST sent back. Okay, so that's what's lying ahead in this module. Now I want to bring up Stellarium here because this is a special week. Here we go. This is Stellarium, and This is set for Thursday, September 22nd. And it's about 3 minutes after 6 in the, I'm sorry, this is about 3 minutes after 5 in the evening. So 3 minutes after 5 in the afternoon. Now, why am I making that choice? Well, that's because this Thursday is the fall equinox, the autumnal equinox. And that is the day when the sun moves from being above Earth's equator to being below Earth's equator. So moving from north to south across Earth's equator. So I set up stellarium here for just a little bit early, a couple hours early. And that's because if I actually went to 3 minutes after 7, that the sun would be setting and we can't see it. So I've backed up here 2 hours, but we can still zoom into the sun. And so I'll do that. So let's zoom into the sun right there. In fact, let me center on the sun. So I'm going to center on the sun. And let's see here. There we go. So there's the sun. And let's really zoom in. And you can see this line going diagonally across your screen is the celestial equator. It's Earth's equator shot into space. And right here on Thursday, the center of the sun is just crossing the celestial equator. And in fact, let me uncenter the sun there. There we go. What I'm going to do is I'm going to go back a day, go back a couple days. So here is Wednesday. Here's Tuesday. And you can see that right now the sun is north of the equator. So here's Tuesday, Wednesday. Thursday is the day of the autumnal equinox, fall equinox. And then Friday, Saturday, the sun dips below the equator. And now there's more darkness during the 24-hour periods than there is daylight. Whereas before, up here, there was more daylight than darkness. And so equinox, same, nox, night, so equal times of day and night this Thursday. So you can celebrate that at 7:03 in the evening. Pretty cool. Well, I hope you enjoy learning all about light here, how astronomers use light. And oh, there's one thing I forgot to tell you. One more thing astronomers can tell from light, and that is how fast a star is moving. How can that work? Well, there is an effect called the Doppler effect. It was discovered by a man named Christian Doppler several hundred years ago for sound. And he put a trumpet player on a railroad car, and that railroad car would move past him. And as it moved past him, that trumpet would play a note. And Doppler noted that the frequency, the pitch, was higher as the trumpet was approaching him and lower as it was moving away. You may have noticed this if you're ever sitting at a train crossing and the train sounds its horn. And it sounds something like this. So the train's over here and it passes you by and its horn sounds like meow. Let me do that again. Meow. Because approaching you, the trumpet or the train was catching up with its own light, with its own sound waves. And those sound waves were compressed and made shorter. That made the pitch higher. Notice the train was moving away from you. It was pulling away from its own sound waves. That was stretching them out. That was making the waves longer. Longer wavelength means a higher pitch. Same thing for light. If a star is moving toward us, it's catching up with its own light waves. As it catches up with its own light waves, those light waves are compressed. And a shorter wavelength means bluer light. And so, an object moving toward us, a source of light moving toward us, will have its spectrum blue shifted. Now, for stars that are close to us in our galaxy, that speed is not enough to change the color of the star. So it's a very small shift, but we can measure the shift in those absorption lines, those lines in the star's spectrum where light has been absorbed. They shift slightly in their position. That means we can measure the star's speed. Same thing if the star is moving away from us. If the star is moving away from us, it's stretching, it's running away from its own light waves. And so we see a redder light. And that's called a redshift. Whereas the light moving from a star moving toward us is blue shifted. So much information comes from starlight. Anyway, I hope you enjoy learning about starlight. As always, if you have any questions at all, you can drop me an email. I can set up a meeting either on Zoom or in my office. I always enjoy talking to people. So I hope you have a good rest of your week, and I'll look forward to seeing you next time. So until then, bye-bye.